please, if you can all get onto Moodle and download these curves, I will show them, but I might be talking about something else while you're looking at these curves. Right, so in the last lecture, we spoke about alpha and eta. That was the ionization coefficient and the attachment coefficient. If an electron moves x, it picks up so many electrons, and that's defined by alpha. So if an electron moves x, then the electrons are e to the alpha x. So it's an exponential growth of electrons. Attachment is similar. If n electrons move x, then it's e to the eta x electrons get removed. So let's have a look at these curves, and we'll start with air. So here you can see alpha in blue, right? You've got eta in red, and you've got the sum of the two in a dotted green. On the y-axis, we have coefficient per centimeter per torr. Remember that it's alpha x, so it has to be, if it moves a centimeter, it's a coefficient that cancels that unit. Right, and then on the x-axis, we have the electric field in volts per centimeter per torr. Guys, could you keep yourselves muted? Could somebody also monitor that for me? Right, so remember that, yeah, that refers to alpha, this refers to eta. Does anybody know what the unit torr is? Nobody. So it is related to pressure. You would have been more familiar with kilopascals or bar. Torr is just another unit for pressure. So what we can see here is that alpha, the coefficient, would also be dependent on pressure. That makes sense? Yep. Right. If we look at the curve, the blue curve, you can see that it's quite small there. That looks like 7 times 10 to the minus 4 at around 25 volts per centimeter per torr. And then what happens as the electric field increases? You can see that it increases as well. Just look at that. I'm going to do it a couple more times. Right, this curve here, that's the attachment curve, eta. Again, you can see it's got a certain value there, and at the higher electric field, it has a different value. Right, so that means it's dependent on the electric field as well. So that also makes sense when we spoke about your drift diffusion equation, your mean velocity of particles. The higher the electric field, the more energy the electron has, therefore it is more likely to cause ionization. That makes sense. Right, if we look at the combination of the two, we can see that below this crossing point, attachment is dominant, right? So ionization may occur, but it is likely that an electron will be attached rather than cause further ionization. If we look above this curve, above this 32 volt per centimeter per torr, you can see that ionization is dominant over attachment. So it is more likely that ionization will occur here. We'll get on to how we use these just now. Right now I'm going to try something a little bit different. I'm going to start something called a poll. So if you all go to Slido in Teams, you can click on which one you think is the best insulating gas, and I'll go through them quickly, and then you should have downloaded them and you can just work with them a little bit. Right, so we've covered air over here. Take note of the units down there. Let's look at nitrogen by itself. Remember that nitrogen is non-attaching. So you'll see there's just an ionization curve, alpha. Right, we can put it side to side with air. Remember that air is predominantly made up of nitrogen and oxygen. If you have a look at the bottom there, let's look at 25 over here. Nitrogen, let's look at 25 in air. You can see it's in a similar sort of region. So that makes sense. Let's look at carbon dioxide. Right, it looks slightly different. You can have a look at your attachment again in red. In the lower electric fields, the attachment dominates. In the higher electric fields, the ionization dominates. Let's look at where it crosses and compare that to air. It is slightly different. Let's look at SF6. Remember that SF6 is a strongly attaching gas. That value there is very different to what we've seen before. If we look at CO2, you can see that the attachment is nowhere near that, whereas SF6 is strongly attaching. Right, you can look at the ionization. Right, and you can also have a look at where it crosses. That looks again different to CO2 and different to air. One thing that you can do with insulation gases is that you can mix them. So this is a 50-50 mix of SF6 and N2. Right, so here you can see the ionization curve, alpha, and you can see your attachment curve. It's got a little bump there because it is a mixture, so it will be slightly different to your pure gas. Right, there's some physics related stuff to that. You can even have a look at that value compared to what you're expecting over here. And again, it's slightly different, and it's quite interesting. Right. Has this poll come up for you guys?
Yes, sir. I have it open. Are we supposed to answer it now?
Yeah, I think if you can all try and answer it, and you can tell me which one you think is the best insulator, and then I can maybe confirm or deny or discuss it. Okay, thank you. All right, it seems the rest of the folk in the meeting either can't answer or don't want to answer. This is not a test. It's just a way to get you to engage. Right, so we see that carbon dioxide is 0%. Yeah, it's not the best insulating gas, but it is more commonly used recently because you can pressurize it nicely. And it is slightly attaching. Nitrogen and air, they're both quite similar. Air has the advantage of oxygen, but it can attach electrons, but it's not the best insulating gas. And then we've got sulfur hexafluoride, which seems to be the choice, and that's probably correct. Just from a gas point of view. And then the sulfur hexafluoride nitrogen mixture, that's a fairly reasonable guess, and I'll show you why. So let's look at sulfur hexafluoride. If you go to the crossover point, you can see it's just a little above 110 volts per centimeter per torr. Let's look at the mixture. The mixture is just above 100 volts per centimeter per torr. Right, so that means that is correct. Sulfur hexafluoride is the best insulating gas here. There was something interesting here where the mixture of nitrogen actually enhances the attachment at the low electric fields. And that's quite important. So they mix the gases. Number one, because you don't have to use sulfur hexafluoride so much. It is damaging to the environment. Number two, which we don't deal with in this course, is that the gas actually the surface of the electrodes has an influence in the way the gas works as well. And the nitrogen tends to improve that a little bit. Right. Let's move on to the actual breakdown mechanisms. Right, we've got three mechanisms that we generally look at. The Townsend or generation mechanism, the streamer breakdown mechanism, and the leader breakdown mechanism. We're not really going to look at the leader breakdown mechanism here. We're going to concentrate on the first two. Right, so the Townsend mechanism, it's generally applicable to short uniform gaps. What I mean by that is that your electric field is uniform. All right, so let's look at our electrodes here. You can see I've got the two black lines. They're separated by a distance d. One has a negative charge, the other has a positive charge or a voltage, and that sets up an electric field between the electrodes. So we start with N0 electrons, and if they move across the gap, we have N electrons, and that's given by your exponential growth. So N0 e to the alpha d. So that's an exponential growth of electrons. They sometimes call it an electron avalanche. Right. The second thing that happens is that all these electrons are moving across the gap. If these electrons are removed from a molecule, you're left behind with positive ions. So they slowly move towards your electrode, your cathode. Right, and what happens when they reach there is that they bombard this cathode with enough energy, because they are moving in an electric field, to release secondary electrons. Right, so that's the third point there, is that the positive ions bombard this electrode and they release secondary electrons. So now we have N dashed electrons released. Those move across the gap. So effectively at D, we'll have N is equal to N0 plus N dashed e to the alpha D electrons. Right, there's some notes here about the energy of the positive ions.
Sorry, sir.
Yeah.
Sir, can you please zoom in or enlarge your screen? I can't see clearly.
Is that okay?
Yeah, it's better now.
Right. So basically, this process is going to repeat itself due to the secondary emission. So again, if we look at 4, we've got that relationship. That will also leave behind positive ions, which will move back and release more electrons. So by definition, we are saying that N dashed is equal to gamma, open brackets, N minus N0 plus N dashed, close the large brackets. So that's an empirical relationship. It's a definition. So this gamma, it's your secondary ionization coefficient, and it depends on a number of things. Your electric field, your pressure, your material of your electrodes. So gamma will differ between aluminium and copper, for example. If we rearrange that equation, N dashed is equal to gamma, and you can see the remainder of the equation there. If we now substitute that N dashed into our original equation over here, you can see that it's taken a slightly different form. And finally, let's rearrange it such that there's only one gamma left. Right, so the top will be N0 e to the alpha D over 1 minus gamma e to the alpha D minus 1. So if we look at the process again, 1 to 4, it repeats until N equals infinity. So that's when breakdown occurs, when there's an infinite supply of electrons. So basically it's conducting. So mathematically, when this term tends to 0, n tends to infinity. Does that make sense to everybody?
Yes, sir.
Right, so we generally say that the sparking threshold is given by gamma e to the alpha d equal to 1. Right, I've just put it like that form, in that form, because that one is often much smaller than that e to the alpha d. Right, so this brings us on to something called Paschen's law. If you recall the sparking threshold given above, or the breakdown threshold, we know that gamma is a function of electric field and pressure. We also know that alpha is a function of electric field and pressure. And we come up with some sort of relationship between alpha d, pressure, distance, voltage, etc. So that F2 is just a function. So we can rewrite the sparking threshold with those functions. And that gives Paschen's curve. Generally, it's empirical for gases. It's very difficult to define that function. You can define parts of it, but it's difficult to define all of it. Right, so let's have a look at Paschen's curve. So this is Paschen's curve for air. On the left here, we have the breakdown voltage in kV. On the bottom x-axis, we've got the pressure spacing product PD. Right, it is an exponential form, but what you can see, for example, over here is it's fairly linear. Right, there are some relationships that we have there as well. So an increase in the pressure spacing product would cause an increase in the breakdown voltage. That makes sense. So the longer the gap, the higher the breakdown voltage. The higher the pressure, the higher the breakdown voltage. Let's talk about what's going on over here. Right. So it's linear over here, and at the bottom here, what's going on here? Any ideas? So it appears, from what I said previously, that the lower the pressure, the lower the breakdown voltage. But then you get to very low pressures, like a vacuum, close to a vacuum, and your breakdown voltage doesn't decrease any further. Any reasons why? All right, there is a reason why. I think you can go back a few lectures and have a look at that. It's particularly related to the pressure, not so much the distance, but I think go back a few lectures and have a look at that. Let's look at our second breakdown mechanism, our streamer mechanism. Right, so this is more common because your gaps are normally bigger. This breakdown mechanism is not dependent on some sort of iterative bombardment. It's more dependent on the number density. And we'll see what that number density is just now. I've given two criteria for the onset of a streamer. This is for the onset of a streamer. It is not the breakdown mechanism. So be careful with this when you write it in a test. So the field at the tip of the streamer must equal that of the background field. And the avalanche amplification must be high, alpha greater than eta. So if your number density, e to the alpha x equals 10 to the 8, or alpha x equals 18, there will be streamer amplification and breakdown. And we can write that differently for an attaching gas. So those are just some info that we're going to come back to. Let's look at the actual mechanism. Right, so again, we've got two electrodes separated by a distance d, and we've got some sort of electric field there. In this case, we're calling it E0. That's the initial electric field. If you look at the graph below it, I've got your electric field on your y-axis and your distance on your x-axis. So that dashed line there is your initial electric field, E0. So the first thing that happens here is the electron avalanche. So it's similar to the Townsend mechanism, but it wouldn't be the main reason for breakdown. Right, so electrons start, you can see there's some sort of avalanche here. Some positive ions will bombard the electrode, release secondary electrons. What do we know about the movement of particles? Electrons are very light compared to ions, so they're going to move much faster than the ions. And I've kind of sketched it here where you can see electrons in the front, and in blue you can see that the ions are just kind of sitting there. So that means that the charge of the electrons is basically separated from the charge of the positive ions. So what do we know about charge? It's proportional to the electric field. So at the front where the electrons are, you'll get a negative electric field, right? And at the back you'll get, you'll get some sort of electric field as well. So this occurs when, so it starts influencing the initial electric field when the number density is high enough. So let's look at the electric fields. Remember that for a negative charge, the electric field goes towards the charge. So you can see the arrow there is going towards the charge. If you combine that with the initial electric field, you start getting some sort of field enhancement. So the electric field has increased at that tip. Right, if we look at the other side, for a positive charge, the electric field would move away from the charge. So in this case, if you look at the arrows again, E0 and your additional electric field, there'll be some sort of enhancement at the tail. In between, your electric field moves from your positive to your negative, so there'll be some sort of cancellation of the electric field. Right, so this enhancement of the electric field, what do you think that's going to do? Remember, ionization is occurring at E naught. So E naught plus an electric field means that there's going to be more ionization. Again, we can go look at our ionization coefficients. You notice that with an increase in electric field, the ionization increased. So with a higher electric field, more ionization will occur. So this essentially leads this streamer to cause subsequent avalanches around the tip, and that causes it to be self-sustained. Once it's self-sustained, breakdown may occur. And that's given by the criteria that I spoke about earlier. E to the alpha x is equal to 10 to the 8. Right, so that's the mechanism that leads to breakdown. These are criteria. So be careful about how you look at these and talk about these. So just before we finish, I want to do one last poll. If you all go to Slido, again, this is not a test, it's just to see that you engaged with the lecture a little bit. And I've got 3 questions there. Please tick whichever one you think is the correct answer. Right, so it looks like it was between two features. The electric field is high enough to cause ionization, got 0%. That's kind of a starting criteria, not the feature of the streamer breakdown itself. The bombardment of the electrodes by positive ions, that's not quite the key feature. It does occur, but it's not what actually causes it. The separation of electrons and ions, and with high enough density influencing the electric field, is probably the key feature. So if we go and look at the criteria, this is the criteria here, e to the alpha x equal to 10 to the 8. So that's the number density. Right, so when the number density, the number of electrons is around there, that's enough to influence the electric field. Right, okay, cool.